Let's now take an example problem and understand what we have discussed in previous few slides. What I want to do is, again, I want to contextualize. Right now, we are just focused on constraint optimization problem, which has an objective function and has an equality constraint. And there are no inequality constraint now yet. We will talk about that in a little bit, but if you have just the objective function and equality constraint, then how can we formulate an augmented Lagrangian problem and how can I solve that optimization problem? So let's take an example and discuss things that will help you in understanding some of the things that we have discussed in previous few slides. So let's take an example problem where our objective function to minimize is this x1 squared plus x2 squared. And if you see the contour of this objective function, which is basically the projection of this function on x1 and x2 axis, the solution is essentially going to lie at 0, 0. If this was an unconstrained optimization problem, the minimum value that you can get out of solving this problem for the objective function is going to be fx equal to 0, and that is going to be there when we have essentially, this will be right here, the center of this will be where we will have x1 equal to 0 and x2 equal to 0. That will be the optimal problem or optimal solution for this problem if the problem is unconstrained. Okay. Now, you can use a Newton's method or you can use a gradient descent method to solve for this problem, and that's what we have discussed. But let's take and make this problem a constraint optimization problem by adding a constraint, and so far we are discussing an equality constraint, so we will add a equality constraint. So now if the objective function that we have here is subjected to this constraint that we have, now this constraint essentially you can see is a linear equation, so this is the line equation. Now you are forced, because your solution to be feasible has to lie on this line. Right? It can no longer be at this location because we have added the constraints. So what happens? So one of the things that I want to connect back, that this is an active constraint, right? Remember, if a constraint is imposed and if changes the location of the optimal solution, right, then it's an active constraint. And in this case, we have added an equality constraint because it is equal to 0, which is essentially the equation of the line. It's an active constraint. So the solution now has to lie on this line. So this is a feasible solution. Okay, this is a feasible solution. This is a feasible solution. Anything that lies on the feasible solution on the line is the feasible solution. Whereas anything that lies here is not a feasible solution anymore because we have added this equality constraint. And we have talked about that the equality constraints are really, really severe, and they really reduce the overall feasibility region of the optimization problem here. So this are infeasible, whereas this, anything that is lying on the line, is going to be a feasible solution that we have. So again, if you look visually, right, what one you can infer is like probably somewhere here is where we will have an optimum location, right? And this is just for a qualitative discussion, but now we have to use essentially a numerical approach to locate that point, right? So how do we go about that, and how do we use this augmented Lagrangian formulation to solve for this class of problem? So let's see that. So what we'll do, we will take this objective function, we'll take this constraint which is in equality form, and from there we will write the Lagrangian first, and then we will write the augmented Lagrangian. Then we will use any optimization approach that we can be using for solving this class of problem. So now let's take this example problem and formulate the optimization augmented Lagrangian formulation for this problem. Okay. So if I take this objective function which is listed here, which is fx and h1 and x, then remember what we need to do is we need to essentially rewrite the Lagrangian formulation. And since we have one inequality constraint, we will have additional new one variable coming into picture, and we will not have this because we do not have two equality functions. In fact, we have only one, so we will have the original x and new one, and this function which is now taking the objective function, writing that up, and then taking a linear combination of this variable new one multiplied by the equality constraint h1, which is one here. So this is essentially, think about this equation is what? This equation is new one multiplied by h1x, right? And that is the Lagrangian that we defined in few slides before. So we take new one and multiply that by h1, and this will be essentially the Lagrangian function. But we do not work on the Lagrangian function. I want to repeat that we work on a slightly modified version which is known as augmented Lagrangian version. So with this formulation, the augmented Lagrangian function will essentially look like this. So it will have the Lagrangian, so it will have this term that is here, right here, but on top of that you will also add this additional term in which you are introducing a new variable r on top of a new one which was already there in the Lagrangian that is here, and you add what? You have essentially a term which is taking the equality constraint and squaring it and then multiplying by r. So if you recall, in our definition of augmented Lagrangian, Rp multiplied by, right, h1 hi x square. So we square the hx square, right? So we are squaring that and multiplying that by Rp. That term is now included here. So this term is essentially the augmented Lagrangian function that we have. Now we take this term and we use this as an objective function, and we use this as an optimization problem, and on top of this now we can use any of the algorithms that we have discussed previously, which is the steepest descent methods and Newton method, to solve for it. The one thing that I want to notice that in the original optimization problem that you have here, how many variables that we have? We have two variables here, right? x1 and x2. But if you look into the augmented Lagrangian, since we had one inequality constraint, we added new one, and then we also added r because we have only one. So now because of the addition of this new one and r, we have two original but two new one and r. So now we have four variables in your optimization problem. Okay, and this is the main change when you take a constrained optimization problem and convert that into an unconstrained optimization problem using augmented Lagrangian. The number of variables increase. Now you have a four variable unconstrained optimization problem which is denoted by this objective function, and here is where you use the gradient descent algorithm or Newton's method to solve for this class of problem. Okay, so I will go ahead and I will also solve this problem in a slightly different way. I will not use the gradient descent approach, or I will not use a Newton's method, which you can actually use once you have the augmented Lagrangian, which is defined by this equation right in the bottom, right? This equation right here. You can take Newton's descent and gradient descent method and solve this problem using those approaches, which you know by now. But I will take a slightly different approach and I will solve this problem in a slightly different way. So again, from the previous, this is the Lagrangian and this is the augmented Lagrangian that we have for the previous problem that we have defined for one equality constraint. And then one of the things that I do, I want to take a little bit slightly, a different approach. If this is the case, right, if this is the function, I can take the derivative of this function with respect to our main variable in the x1 and x2, and I can write their derivative, which is right here. So I differentiated this function with respect to x1 and x2, and that is essentially denoted by this function. This is derivative of the augmented Lagrangian with the variables in the original optimization space, which is x1 and x2. So I write that, and if I equate that equal to 0, I know when we take a function and we take the derivative of that function and equate that equal to 0, we find out the optimal solution, because that's where minima or maxima should lie. And that's what I'm taking. I'm taking sort of a semi-analytical approach to solve for this problem. And here is the analytical part where I'm taking the derivative of the augmented Lagrangian and equating that equal to 0. So if that's the case, I have two equations. I can solve for this and I can eliminate two of the variables, and I can have an iterative loop just to optimize for nu1 and rp, which I will show you quickly. So if that's the case, I can solve this two equation, and from this two equation I will get this x1 and x2 is equal to 2rp minus nu1 divided by 2 plus 4rp. That will be the solution. Now what we can do is we can assume some starting value. So if you look into the overall, the steps of solving the problem, you have to assume some values of rp or news. So that's what we are going to do. Now we are going to assume rp equal to 1, nu in the new one, which is the only variable that we have in the iteration 0. So that's why here we have this. So this is an iteration index, or let's call that q index. This denotes the iteration, and the new one that denotes essentially the the number of the equality constraints. Since we have only one, so this will be 1, whereas this index, which is new 0, 1, 0 will be changing in the iteration. The next iteration it will become 1, next iteration it will become 2, and so on. That's how it's going to be changing. So let's see, if we assume these two values, then how we can solve this problem semi-analytically. Okay. So from there, if we choose this, then I can substitute the value of Rp equal to 1 here, and new one 0 is 0 here, and I can solve. And in the first iteration, the values of x1 and x2 is going to be equal to 1 by 3. Okay, and then from there, essentially we can solve we can see what is the value of h1x. This is 1 minus 1 by 3. So again, this solution is not satisfying the equality constraint, because when the solution is there, has to be close to 0, because this is an equality constraint. Since this is 1 minus 1 by 3, it is not equal to 0, or even it's not close to 0, so this is not a good solution. And then we remember the iterative schemes that we have for new, that could be updated using this equation that we have. So now we have computed this h1, which is minus 1 by 3, and what we will do, this will force the overall solution to come closer to the equality constraint. So now when we compute the new for iteration 1, and we have only one equality, that's why this is there, we will take new 1 0 plus 2 Rp hx. So that's what we have substituted, and from there we get a new value of new in the next iteration. Remember, here it was 0, but in the next iteration the value of new 1 is becoming minus 2 by 3. So now we take from there and we keep iterating the different solutions that we have. So if that's the case, again, there are multiple different methods that you can use for update. The update I was showing there, you can either keep vk equal to 0 in each iteration, and this is how you can begin, and that's what we are using, in some of that. Or you can have another one where vk can be set equal to 1, right, if this condition is satisfied. So there are many different ways to initialize that. We are using one of these ways in our overall problem that is out there. Or you can use this also, if this is the case, right? So let's continue our example, and let's move on to the second iteration. For Rp equal to 1, we have calculated the new value of new. Now we substitute Rp equal to 1 and new equal to minus 2 by 3. So that's what you will see is computed here. Minus 2 by 3 is something that has been computed. We will now use this new value and Rp equal to 1 in the iteration 2, and that will give me the new values of x1 and x2. So you can see that we have Rp equal to 1 and new equal to minus 2 by 3, that which we have computed. Substitute that, and now x1 equal and x2 equal to this is what we will have. So now you can see we have an iterative scheme, a semi-analytical scheme, where we are moving from different values for x1 and x2 in previous iteration to new, and now we will be also checking the 3 convergence criteria, whether we have satisfied those 3 convergence criteria or not. If those 3 convergence criteria has not been satisfied, then we will loop again and we will run this iterative scheme going forward. Okay. So here now in this case, you will have hx equal to minus 1 by 9. Again, you will compute a new value of new, and that will be minus 8.9. And from there, Rp equal to 1 and new equal to minus 8.9. What we will do, we will compute a new value of x1 and x2. And this is how the iteratively x1 and x2 computation can carry on. So that's what I have listed here in a tabular form. When you have this iteration, Q is iteration index 1, 2. This is the calculation that I have already shown you. But you can carry on this iteration 3, 4, and 5. And you will be getting this modified values of new in each of this iteration. x1 and x2 are going to be same, but the value in each of the iteration is going to go here. Now you can see the value of the equality constraint, which started with minus 0.333. Now it's going to minus 0.00, which is becoming closer to 0. That means the solution is now actually also ascertaining the feasibility of it. And this is the iterative scheme you will use. And this is the table form that you will get, and then you will see whether you have satisfied all the convergence criteria or not. And if you have satisfied the convergence criteria, then you will stop in the iteration index in which you satisfy the convergence criteria. So this is an example where we started with a new value of 0, right? And that's how we move forward. But here is another example. If you chose new value to be -2 in the first iteration, then you might have a scheme like this where you start from -2 and you're going in this direction and your solutions are moving in this direction that is on. So with different values of new, you can try out and you will get a different set of slightly different type of convergence, different way, different location. But this is how the methods will overall work. Now I have shown this example problem in a semi-analytical way, and why I say this is a semi-analytical, what we did is I used this information, right, where I took the derivative of the augmented Lagrangian with respect to x1 and x2, equated that to equal to 0, and then I used which is the analytical portion, and then we have essentially an iterative scheme for solving for iterative of doing new and RP update. So that was the iterative scheme. So that's why this approach is a semi-analytical, and this is an approach that is typically not used, but I just did that so that you can understand several concepts. What you will typically do is you will take this Lagrangian, augmented Lagrangian, not Lagrangian, augmented Lagrangian, and then you will use essentially a steepest descent method or a Newton method to solve for this problem. And you will check on the convergence criteria whether you do have satisfied, and that will be the proper way to numerically solve this overall problem. Okay.